Hi, good morning everybody, and welcome to this morning's webinar from Pilz, Understanding ISO 14119 Interlocking Devices. My name is Jason Reed and I'm one of the account managers here at Pilz. You can type your questions or any questions that you may have using the toolbar on the right hand side of your screen, and my co-hosts in the background, Alex Bryce and Andy Maskell, will try to answer these during the course of the webinar. If for any reason they can't, then we'll contact you shortly afterwards with any answers that might be remaining. The webinar is being recorded and a link to the recording will be sent to you shortly after the webinar has concluded. The presentation is also available, and if you'd like a copy, then please ask in the questions section. And there's also a couple of handouts today around safeguards and stock manipulation. That you can also download, and I'd also point out that any product references today will be yellow in colour and from Pilz. So the agenda for today, there'll be an introduction and a structure to 14119. I'll run through different types of interlocking devices, the selection of guard locking, defeat of interlocks and measures to prevent it. We'll run through fault exclusion, fault masking, how it occurs, quantifying its impact on diagnostics coverage, and hence the achievable level of safety, how to overcome it using various means and technologies, and then we'll close just running through future webinars from Pilz. So just a recap really of standards and the structure. So standards are broken down into three tiers. A standard specify fundamental concepts, terminologies and principles, of which there's only one, which is ISO 12100, which is general principles for design, risk assessment and risk reduction. You then have B standards, which deal with certain machinery safety issues or certain types of safeguards that can be used across a wide range of machines. i.e. 14119, and then C standards contain specifications for certain individual machine groups. So in line with 12100, if the risk has not been adequately reduced, then we look at risk reduction by protective measures. First, we go to inherently safe design measures, and then we look at safeguarding and complementary measures, which is why we're looking at 14119 and where interlocks sit, and then finally we'd have information for use. Presumptive conformity to the Machinery Directive came into effect on the 30th of April 2015, and in the UK this would now be the Supply of Machinery Safety Regulations 2008, and this standard is relevant to anyone that manufactures interlocking devices or uses interlocking devices. So OEMs such as Pilz, OEMs of machines and end users. So how is the standard structured? I'll run through the clauses here, but we're going to go into more detail with some of them within the presentation. So clause 1 is the scope, so what it covers. Clause 2 is the normative references, making reference to other standards such as 13849, 14120, for example. Clause 3 is terms and definitions, so that's a glossary. Clause 4, operating principles and typical forms of interlocking devices associated with guards, and we'll look at this in more detail. Clause 5, requirements for the design and the installation of interlocking devices with and without guard locking, so fastening, switch and actuators, actuation modes, how it interfaces to the control system. Clause 6, selection of an interlocking device. Clause 7, designed to minimise defeat possibilities of interlocking devices. Then we'll look at motivation to defeat in more detail later on. Clause 8, control requirements. So it looks at common cause failure, fault exclusion, series connection of interlocking devices, and again we'll discuss this in more detail. And clause 9 is information for use, which is given by the manufacturer of the interlocking device, i.e. Pilz, or by the manufacturer of the machine. Excuse me. So types of interlocking devices. So table 1 provides an overview of interlocking devices, interlocking types, with a cross-reference to examples in the standards annex. So an example of that would be if you look at mechanical actuation principle, physical contact or force. If we looked at coded as the actuator example, and we looked at tongue-shaped actuators, that's type 2, then you'd find that in annex B1. So if we look at mechanical, you've got cam and hinge type, they're uncoded and they're type 1. And examples would be the direct acting roller or a plunger limit switch. You've then got mechanical tongue-shaped actuators or trap key systems. These are coded and they're class 2 type. You've then got non-contact, which are broken down into inductive, capacitive or optic. They're uncoded and they're type 3. And they're generally not safe enough for interlocking guards due to the lack of coding and ease of bypass. And then finally, you've got magnetic and RFID, which are coded and type 4. There's 3 levels of coding. So we have low level, which are for 1 to 9 variations of code. We have medium, for which there's 10 to 1,000 variations in code. And then we have high level, for which there's more than 1,000 variations of code. High covers uniquely coded RFID systems, medium covers trap key systems and some limited RFID systems, whilst low covers magnetic reed switch types and reteachable RFID systems. So when selecting an interlocking device for a machine, it's necessary to consider all phases of the machine life cycle. So selection shall take into account, but not be limited to, the following criteria: the conditions of use and the intended use of the machine, the hazards present at the machine, the severity of the possible injury, probability of failure of the interlocking device, overall stopping performance and access time, the required performance level or safety integrity level of the safety function, and for type 4 interlocking devices, the means to avoid that a single actuator can be taught in an unlimited manner by the operator without special knowledge and a special tool. And again, we'll discuss that in a bit more detail. So if we look at the flow chart for the overall stopping performance and access time, and we'll refer to 13855 for this. If the overall stopping performance is less than the access time, then that means that we can use an interlocking guard without guard locking. So the hazardous machine function covered by the guard cannot operate until the guard is closed. And if the guard is opened while the hazardous machine functions are operating, the stop command is given. And when the guard is closed, the hazardous machine function covered by the machine can operate, but the closure of the guard does not by itself start the hazardous machine functions. And again, if we use the flow chart, if the operating system stopping performance is greater than the access time, then we would use interlocking guard with guard locking. So it may be a mixer with I don't know, rundown time, inertia. You need to wait for that to stop before you can actually open the interlock guard. So the guard remains closed and locked until the risk due to the hazardous machine movements has disappeared, and the hazardous machine functions cannot operate until the guard is closed and locked. And when the guard is closed, the hazardous machine functions cannot start on the closure of the guard itself. So defeating safeguards and manipulation. So ISO 14119 stipulates that the machine shall be designed in such a way that it minimises the motivation for defeating the interlocking devices, and goes on to stipulate the interlocking device shall provide the minimum possible interference with activities during operation and other phases of the machine life in order to reduce any incentive to defeat it. And why is this important? Well, a report was carried out by a German test house, and its findings were that 37% of safeguards are manipulated constantly or occasionally. And that 25% of all accidents when operating machinery can be attributed to manipulation. So a quarter of all machinery operated accidents were caused by manipulation. So the machine shall be designed in such a way that it minimises the motivation for defeating the interlocking devices. That's the 12100. The interlocking devices shall provide minimum possible interference with the activities during operation and other phases of the machine life. Then we use the following procedures in order to avoid interlocking devices being defeated. So we use this flow chart to minimise defeat. So we start, we implement basic measures, we see if there's a motivation to defeat. If there isn't, we can end. If there is, then we look to see if it's possible to eliminate or minimise the motivation to defeat. If not, we implement additional measures. If it is, we implement design measures or alternative modes, and then we go around to look to see whether motivation to defeat still exists, and it's a loop that you continue. So we'll go into those into more detail. So use of basic measures. The fastening shall be adequate, so they should be reliable, and loosening them shall require a tool. Self-loosening shall be prevented. Forced opening of the interlock must lead to a reaction, i.e. damage or equivalent time-consuming measures, so it could be a temporary restart. The device shall be selected in order to be able to withstand the expected forces. Dynamic effects like bouncing or chatter should be considered because we're not always careful when closing doors or guards. So the impact of a door being slammed closed really needs to be taken into account and not affect the operation of the interlock during its life. And we must avoid Type 3 interlocking devices unless shown in a risk assessment due to the lack of coding and the ease of bypassing. So, you know, you could put a screwdriver in front of it, for example, and trick it to thinking that the guard is closed. Now we've implemented basic measures, we need to check whether the motivation to defeat the interlocking devices in a reasonably foreseeable manner still exists. So we can use clause 5.2 in ISO 12100, which is considering experience of use, along with table H1 in the annex of 14119. So table H1 gives the most common operator tasks versus the respective benefits when defeating the interlocking device. And H2, as shown in the slide, gives examples of an evaluation of motivation to defeat interlocking devices on the machine. So if there is a motivation to defeat, can we eliminate or minimize? The motivation to defeat can be avoided by implementing alternative operating modes. So if we introduce modes of operation, this can make the interlocking device unnecessary or unattractive. So by introducing permission keys, such as a PIT gate box with PIT reader, we can restrict operating conditions to authorized and trained personnel only. So only the trained and authorized person can operate the interlock and stop the machine. You may wish to run the machine at a reduced speed during setup mode or in line with an enabling switch to-hand control, or use an incremental encoder to determine safe speed position and speed, safe position and speed. This allows trained and authorized personnel to work safely within the machine's danger area without defeating the interlocking device. And so for safe operating mode, you can see our PIT reader here. It can be used for both security and for safety. So in this case, we're looking purely at safe operating mode, and we can select automatic mode, number 1. Number 2 would be setting mode. Number 3 would be manual intervention. Number 4 would be a special or process monitoring, and number 5 would be a service mode. So this means that only the trained, authorized and competent operator can potentially bypass the machine or put it into a different mode safely without the need for defeating. And if they were to remove their key from the PIT reader, then the machine would automatically default back to automatic mode, and so all your safeguards would kick back in. And so in this example here, we've got groups of machines. So we've got machines 1 and 2, which is device group 1, and then we've got machine 3, which is device group 2. We've got all our safe operating modes in position, both on the left and the right. And then we have our key, which is in this instance could be my key. So for device group 1, I have access to all 5 permissions, but for device group 2, I can only do permission number 1 because of my my training and my competency, etc. 7.1d, additional measures are required if defeat in a reasonably foreseeable manner remains. So if the possibility of defeat cannot be excluded through modified or additional operating modes, only one element really remains to the design engineer, and that's to make it more difficult or impossible to defeat the interlock itself. And so a way of doing that would be to install them out of reach, physically hide them so you can't see that they're there, use barriers or screens, and as I said, install them in a concealed position. Prevent substitute actuation of the interlocking device by means of an object that are readily available. So we do this with the use of coded actuators. And as mentioned earlier, low coding covers magnetic reed switch types and reteachable RFID types. Medium covers trap key systems and some limited RFID systems. High covers uniquely coded RFID systems. So what does this look like for Pilz and our products? So we have a number of products with RFID coding, and we break these down into what we call coded, fully coded, and uniquely coded. And so coded just means that we supply you a pair, a switch and actuator that are coded, but if you were to damage the actuator, you can buy a replacement from Pilz, and you can just install it and use it. We do, so that's low coding. We then do fully coded, which means that we supply you a pair, so we apply you a switch and actuator. If you were to damage the actuator, then you can teach a new actuator up to 8 times, and on the 9th time, both the switch and the actuator would be defunct. You wouldn't be able to use them. So that's where we discussed earlier about type 4 interlocking devices and the means to avoid that a single actuator can be taught in an unlimited manner by the operator without special knowledge or special tools. And then finally, we do uniquely coded, where the switch and the actuator are sold as a pair. And if either are to fail, then you have to buy a new set. The use of caps or permanent fastenings, which Pilz can supply, and prevent defeat via the control system. So if we look at status monitoring, the plausibility testing detects during machine cycle any unusual successions of state resulting in defeat. So for instance, the control system expects the opening of a door in a defined machine cycle. The absence of the control signal indicates defeat. An example may be that the actuator has been removed from the door and left in the interlock. The door can be opened, but the interlock is bypassed. And then we have periodic tests. So for infrequently open guards, ISO 14119 stipulates a test once every year for PLD and once a month for PLE. So the safety controller within the real-time clock that's embedded will ask the operator to actuate the interlock, and failure to do so would prevent the machine from startup. Fault exclusion. The use of fault exclusion has long been covered in EN 62061 in the technical paper 23849, and also in ISO 13849, and relates to a single mechanical point of failure, i.e. the tongue or the can. and it can not be fault excluded for PLE systems by the user. This limitation to PLD for fault exclusion appears in 14119. And in the example here, we have our PCEN MEC interlock, which is PLC rated. That's the unit on the left-hand side. The actuator is the single mechanical point of failure. And by using the PCEN bolt on the right, the image on the right, we can claim fault exclusion as the actuator is less likely to fail due to the over-dimensioning of the PCEN bolt. So we can therefore claim PLD to the unit, to the interlock. So to achieve PLE, especially for guard interlocking, the use of at least 2 devices is necessary unless the user uses a PLE certified guard locking interlock device where the manufacturer states maximum extraction force. And in Pilz case, the interlocking is done electronically via RFID in the tongue of the actuator, and the solenoid is bistable pulse to lock and pulse to unlock. The manufacturer of the guard locking device shall ensure that in the engaged position, the guard locking device withstands at least the specified holding force, F. The manufacturer shall specify a holding force which shall be less or equal to the holding force. So the holding force must be 3.1 times specified holding force. And you can see that the holding force of our products on the list below, albeit for the S-lock, which is a magnetic lock that we use, that's generally a process lock and not for personnel protection, as it operates on energized to lock principle. So it would not lock, it wouldn't be locked in the event of a loss of power. Fault masking. So clause 8.6, logical series connections of interlocking devices. Logical series connections of interlocking devices means for normally closed contacts wired in series, or for normally open contacts wired in parallel. And when interlocking devices with redundant contacts are logically connected in series, the detection of a single fault can be masked by the actuation of any interlocking device logically connected in series with a defective interlocking device to the safety-related control system. It is therefore foreseeable that during the fault finding by the operator, one of the guards whose interlocking devices are logically connected in series with the defective interlocking device will be actuated. But in that case, the fault would be masked and the effect of the diagnostics coverage value shall be considered. And 24119 deals with the logical series connection of devices, and the diagnostics coverage, the ability to detect dangerous failures, is expressed as a percentage. So 24119 evaluation of fault masking serial connection of interlocking devices associated with guards with potentially free contacts. And this is a technical report that is dealing at a specific case of how to deal with the serial connection of interlocking devices, the influence on the diagnostics capabilities of the safety interface. And DC equals a diagnostics coverage, and that's the ability to detect dangerous failures expressed as a percentage. And as there are a number of existing machines that have been in service for a number of years on the on the market, it's worth considering fault masking for these and new machines. So the following slides will show how this can occur. So in this instance, we have 3 gates, all wired in series back to a safety relay. Let's say it's a food production line, and at the end of each shift or at the end of the day, it's washed out. So as it stands, all guards are closed, and the safety relay sees no issues, and the machine is running. Excuse me. For some reason, the operator needs to open guard 1. It could be due to batch misalignment, for example. When they open guard 1, channel 1 opens, but channel 2 is defective and remains closed. You can see that here. channel 1 opens, this is closed. The safety controller switch is off to stop the machine, and the machine is in a safe state for now. Once they've cleared the misalignment, the operator closes the guard, but channel 2 is defective. The safety controller does its job, detects the fault, and prevents the machine being reset. And again, the machine is in a safe state for now. Due to time pressure, or the operator might know how to overcome guard 1 issue from prior experience, but not necessarily understanding the safety repercussions. The operator goes to guard number 3 and they open it. When they do this, channel 1 and 2 both open, which is what the safety relay is looking for, and thinks that the fault is cleared. The machine at this point is still not in operation. So guard 3 is now closed. Channel 2 fault on guard 1 is now masked. The safety controller is enabled. The machine can be started with the mask fault hidden. So due to the washdown over time, channel 1 on guard 1 also fails. Safety controller is enabled. The machine can be started with fully dysfunctional guard. And so when guard 1 is now opened, the safety controller does not recognize the guard state. Due to the failure of the 2 channels, the contacts remain closed and the machine continues to run with the guard open. This is a loss of the safety function. So now we're going to look at diagnostics coverage, common cause failure, and performance level. So how can we control the likelihood of a loss of the safety function? Well, the likelihood of a loss of the safety function is made up of many contributory factors. So it's a bit like rolling a dice to see which might fail. And it's made up of the architecture, detection of the fault to be able to react to the faults, that's the diagnostics coverage, the reliability of the components, common cause failure, and systematic failures. So, you know, these are down to human error, so that could be how it was installed, etc. So it's worth pointing out that the architecture and the fault detection capabilities are linked. So the DC comes from the functional safety standard, of which there are many. However, for machinery safety, we look at 13849, and common cause failures from different items resulting from a single event, where these failures are not consequences of each other. The chance of a dangerous failure is not only based on the reliability of one component, but it depends on the total loop. So all the parameters which we design are effective on the total calculation, and it depends on the whole structure. So diagnostics coverage measures the effectiveness of the diagnostics, which may be determined as a ratio between the failure rate of detected dangerous failures and the failure rate of total dangerous failures. And bear in mind that diagnostics coverage can exist for the whole or parts of a safety related system. So for example, diagnostics coverage could exist for sensors and or logic systems and or the final elements. So the ability of a safety function to detect within itself a dangerous failure is expressed as a fraction or a ratio of the dangerous detected failures versus all dangerous failures. So diagnostics coverage equals all dangerous detected failures divided by the sum of all dangerous detected failures and all undetected failures. And that is given as a percentage. So how do we determine the performance level required? So we need to look at the chart that we see here. So we look at the starting point for evaluation of safety functions. So S1 is slight, so it's normally reversible. So that could be a scratch, bruise, a light wound that's requiring first aid. And S2 is serious, so normally irreversible injury or death, which is pretty much irreversible. So in this case, we're going to say that we'll look at S2. We then go on to the frequency and the exposure time of the hazard. And so F1 is seldom. so it's seldom to less often, and or the exposure time is short, so that's less than once every 15 minutes, and or an accumulation exposure is less than 1/20th of a shift period, and F2 is frequent to continuous, and or the exposure time is long, so that's more than one every 15 minutes, and or accumulated exposure is more than 1/20th of a shift period. And in this case, we're going to say F1. And then we have to look at the possibility of avoiding the hazard or limiting the harm. So P1 is possible under specific conditions, and P2 is scarcely possible. And in this case, we'll say P2, and that would give us an overall performance level as D. So we also need to understand the categories and the behaviour under single fault conditions. With regards to categories, we have category B, so a safety function can be lost in the presence of a single fault, realised by a single channel. Category 1 is as with B, but less likely because we're using well-tried components than its single channel. Category 2 is as with 1, but less likely because we're using periodic testing, well-tried principles, but it's still single channel. Category 2 is a single fault, ideally detected, won't cause loss of the safety function. The second fault can cause loss of the safety function. We use a redundant structure as well as well-tried principles, so this is dual channel. In category 4, neither a single fault nor an accumulation of faults cause loss of the safety function. Single faults must be detected, redundant structure and cross-checking, and well-tried principles. And again, this is dual channel. So why is the performance level? X is the category level, and the DC, which is why they're all interlinked. So our mean time to dangerous failure, MTTFD, is low, being green, medium being yellow, and high being red. And this chart is intended mainly for designers to evaluate how they could achieve the desired performance level. It's not intended to verify which performance level has been achieved. So if you wanted to achieve PLD, then you need a minimum diagnostics coverage for category 2 or a low diagnostics coverage for cat 3. And this can be impacted by fault masking. So it's kind of worth pointing out that you can't just choose an interlock to performance level D and expect it to achieve that unless you look at the architecture, the diagnostics coverage, common false failure, etc., that's all connected to it. So TR 4119, which was mentioned earlier, uses a simple method to look at maximum diagnostics coverage. It's made up of 3 columns, so the number of frequently used movable guards, the number of additionally movable guards, and the maximum achievable diagnostics coverage. And by frequently, we mean it opens at least every hour, but as soon as you have 2 switches in series, then the maximum diagnostics coverage you can achieve is medium. But in any case, if multiple movable guards will be opened at the same time as part of a normal operation, or say service, could be to clean the machine at the end of a production run, then it's foreseeable that fault masking will occur and the diagnostics coverage is limited to none. So how do we overcome fault masking? So we can look at independent circuits back to the panel. So we individually wire interlocks and other fault-free contact devices such as e-stops directly into individual safety relays or modular safety relays and create hardwire logic without software between the safety relays as required. And if need be, we can tie them together. We can also wire them into individual inputs on software configurable safety controllers with multiple inputs. We can also do zone-free switches, which are existing into small groups. So individually wired guards or zones as below, we can use our Pilz PDP-20 unit, which has test pulse outputs, OSSDs, so they're output signal switching devices. This avoids the need to rip out switches by monitoring existing switches individually via a four-way gate arrays, and they're linked back to one safety relay. So they look like a safety relay, but they have 8 input channel units that monitor up to 4 switches, and as long as all channels are healthy, it gives you an output that you can wire back to another PDP-20 unit, monitoring additional devices, or back to the safety relay. So instead of removing existing volt-free switches that you've got on an existing machine, you can add these PDP-20 units to your machine, which will minimize the change of switches, reduce cost of cabling, and improve safety up to PLE per switch, as 99% diagnostics coverage can be claimed. We can wire them back into small groups, so individually wire volt-free contact-based interlock switches, e-stops to PDP-20 mag units, which uses test impulses on each dual channel device for short circuit detection and checks similarity, and has test pulse outputs, which can be cascaded to other PDP-20 units. So if we look at our machine, we've got X1, which is looking at 4 individual switches to make sure they're all healthy, and the output is going to the inputs of X2, which then has 3 switches wired into it, and the output of which is OSSDs is then going to the safety relay, which is then used to control the main access on the machine. They can be used for all fault-free switches, such as interlocks and e-stops, and this is an example of how it would be wired. They have a very high input impedance, which means that you can cascade over hundreds of meters or within a panel as a digital input expansion. If a series of interlock switches is required to meet PLE, using switches with integrated fault detection can overcome fault masking. So interlocking devices featuring OSSDs outputs with a microsecond off pulse fault detection and inputs with plausibility cross-checking built in are unaffected by fault masking. So the switch is checking the output of the switch. So this is this switch here is checking the output of that switch, which is then checking the output of that switch, etc. Back to the safety relay, and they come in different shapes and sizes depending on the application, and the actuator can be mounted in various positions and forms. And we've also have the world's smallest low profile actuator, which can be used with an adhesive to locate it onto the machine. And if it's peeled off, then that would destroy the actuator, so it can't be used. And so although performance level is unaffected, reaction times should be considered carefully. Each safety switch has an intrinsic reaction time or risk time. And for Pilz, that's a maximum of 260 milliseconds. And each safety switch also has a delay on de-energization time, propagation time, to process the incoming OSSDs from the previous switch, and for Pilz that's a maximum of 20 milliseconds. The function of the furthest away switch has a resulting reaction time equal to its own intrinsic reaction time, plus the sum of the propagation times of all the switches and safety relays downstream. So the example here is that if we look at 4 guards, 4 switches, if we look at switch 4, the total reaction time for switch 4 is the safety function is equal to the reaction time of switch 4 plus 3 times delay at each input of each switch, plus the reaction time of the safety relay. So that's 260 milliseconds plus 3 times 20 milliseconds plus 20 milliseconds for the original switch. So that would give us a delay of 340 milliseconds. And we need then to consider that for a safe distance between that end of line guard 4 and the hazard in accordance to the stopping time of the machine. So S in this case would be the minimum distance from the hazard in millimeters. K is the human approach speed. T is the total stopping time of the machine in seconds. And C is an additional distance based on the device topology used. So the types of Pilz products that we have with RFID technology with OSSDs, these are just links that you can look at at any time after the webinar. So we have our PSEN CS range, our S-locks, S-gate, and then we have our ML locks with guard locking and unlocking. You can also use distributed fail-safe inputs into a safety relay via passive IP67 rated input modules. The Pilz PDP67 units operate with 8-pin OSSDs, base safety switches, such as our PSEN CS RFID coded switches and our PSEN S-locks, and they are effectively a series connection box. Alternatively, you can connect distributed fail-safe inputs into programmable safety relays, such as a PNOS Multi-2, via active IP67 input modules. So these PDP67 modules can be used with all safety sensor types, contact-based or OSSDs, and the PNOS Multi using IO-NetP modules. So the benefits of this are high level of safety, up to PLE, long cable runs up to 1,000 meters. You can reduce the field cabling and panel space, reduce installation times, less cost, local diagnostics, rapid commissioning and fault finding, and then you've also got the future expansion for modular machines. So an example would be a PNOS multi-based unit with 4 PDP link modules, then up to 4 PDP67 field blocks per PDP link module. And you can have up to 4, so you could potentially have up to 64 dual channel sensors connected. And where voltage drops occurs, we can provide extra power via the use of a high power version of the PDP67 field block. If we have very large numbers of safety inputs over long distances, then we can use a safety PLC and remote IO. So we can decentralize extremely large numbers, hundreds or thousands of safety input circuits using what we call IP20, IP67 remote IOs, such as that found in our PSS 4000 system, and distributed safety using SafetyNet-P protocols. And either over Ethernet copper cabling, which is limited to 100 meters, or we can do this over copper and fiber optic cables and network switches. So based on what we've ran through so far in the webinar, is this an acceptable interlocking device? So okay, we don't know the performance level required, but we can see by the fixings, that they've come loose. They've either been taken out and deliberately removed to bypass, or they've come loose over the life of the machine. We've got potentially fault masking. We've got a single point of failure on the actuator itself, so maximum PLC. How long has it been in service for? It may have reached the end of its life, its mission time. So there's lots of things to look at and to take into effect. So the types of interlocks available from Pilz, we've kind of ran through these. These are for you to look at really at your leisure later on. But we have our PSEN MEC range, which are for covers, flaps, swing gates, sliding gates. They're normally de-energized. So you've got electromechanical, therefore personnel protection and process protection. And as discussed, used on their own, they're fault PLC, but if you use them with the PCN Vault, you can claim fault exclusion to PLD. We have our PCN S-Lock range, again for covers and flaps, but that's typically for process protection up to PLE because it's a magnetic force that retains it. We have our M-Locks, which is a bistable principle up to PLE, likewise with our PCN gate interlocks. So we have discussed this at the last webinar. There is a new version of 14119 on the way. It keeps getting pushed back. It will basically introduce a new type 5, which will be purely for trap key systems. So they'll have their own separate group as opposed to being classed as type 2. And as a result, there'll be a lot more detail on trap key systems with a lot of input from trap key manufacturers. And there'll be further guidance on fault masking scenarios, which will be included in 14119, not just separate in 24119. And as and when that new standard is released, we'll then do an updated version of the webinar. So yeah, all that's left to say is that all previously recorded webinars can be found at our go-to stage. We've got various topics ranging from cybersecurity, CE, UK CA marking, safe human-robot collaboration, and they can all be there. You can have a look at those at your leisure. The next webinar is on safe radar systems, excuse me, and optoelectrical sensors and technology for greater productivity, and that's going to be around on the 27th of May. Yeah, I'd just like to say thank you all for attending today's webinar. I hope you found it useful. If there's any information that you require, then please contact ourselves at Pilz, and we'd be